Okay, today I'm really excited. Until now, a lot of the code that I've been adapting and creating has been pretty crummy. And, although I have been able to, more or less, achieve the results I was trying to get, the implementations were not the best. Over the last couple days, I've been getting more familiar with the aleph-DSP directory. And I think that gaining an understanding of the code in here, and becoming able to implement it will not only allow me to level up in terms of coding, but help me to unlock more of the functionality of aleph, and begin to implement ideas better in the future. So, even though today's video primarily deals with how to create a state variable filter for aleph, I would also like to begin discussing the components of the aleph-DSP directory and a general method for understanding them and interacting with them to create less crummy, more interesting modules. To start, I have the aleph-DSP directory open on GitHub here. And a brief investigation seems to indicate that it is a collection of pre-built code for filters and delays and other things. I guess I would like to mention the idea from a previous video about BSOPs being like C functions, and how using them is a bit like building a pseudo-C program. In this case, you can use the functions in the files from aleph-DSP, like pseudo-BSOPs, to build a pseudo-BS network with C code. You have pre-built modules that you can plug in where you need particular functionality, and the best thing about all of this is, looking into the theory behind how to create, for example, a digital filter, it gets very difficult very quickly. So, what monome and the collaborators on aleph have essentially done is not only to give us pre-built modular blocks that we can use to unlock more functionality, but also templates to gain a better understanding of how the, for me, extremely difficult theoretical principles get translated into functional code. And there are so many things that a user could do with that knowledge. One thing that I'm really interested in lately is VCV-Rack. Looking at the code repositories for the modules indicates that there are a lot of commonalities and opportunities for crossover, so it's another case where the concepts gained by working with aleph, especially as we're progressing to a slightly more advanced level of looking at the blocks of code in the DSP directory and figuring out how to implement them, are going to be applicable to an unbelievable amount of other projects. While there are a ton of benefits, there are also some challenges. I guess the biggest for me is that sometimes it can be a little bit difficult to use or implement the code. Mostly because, for me, some of the concepts from C that it's making use of are intermediate or advanced concepts that, while I understand what they are, I've never used them or seen practical use cases until now. I think the most difficult parts are getting into the right mindset, i.e., removing the layers of abstraction from how I think about things, like filters, and getting the syntax right so that I can actually get the functionality that I want. So, in addition to talking directly about today's topic, the state variable filter, I would like to talk about the strategies that I've come up with so far to deal with these challenges. I realize that some of these may be incomplete, and that those familiar with aleph, DSP, or just C in general may have better ways of approaching the same issues, but I guess for me, without a formal tech background, this is the best way I can figure out at this point, but I hope to continue developing my understanding and becoming able to explain better. I would like to start by examining a couple concepts in C, mainly structs and functions. I would also like to talk a bit about header files and how they relate in general, but more specifically in this case. At this point, I would also like to mention that there are a lot of other channels that focus exclusively on C programming, and I really recommend those, especially Caleb Curry, for much better, more complete coverage of the concepts I will briefly cover in this video. Okay, I think the first thing to do is a really brief examination of struct, just because that will help to frame one method of thinking about and interacting with the files/code in the DSP directory. This handy page I found says that structure is a user-defined data type available in C that allows users to combine data items of different kinds, and that structures are used to represent a record. It uses the example of books, and this is a pretty typical example. Scrolling down, it also gives us an example implementation. We have struct books and it's made up of title, author, subject, and book ID. The first time I encountered this, I understood the concept, but wasn't really quite sure how it could be used, other than for a database-type application. Examining the aleph code, especially in Bs and in the DSP directory, the first thing I noticed was a lot of structs. Structs are a huge part of the aleph code. I guess I could understand why a struct would work for books or students, but I had a lot of trouble at first with trying to see why this would work for aleph. I guess the idea that I came up with recently was that a struct is essentially a container, and the elements of the struct are subcomponents that add details or functionality to the container. For example, if the struct, or container, was a blank synthesizer module, then the elements it contains would determine what type of module it was. A delay would need wet, dry, time, and feedback elements, or controls. An oscillator might need coarse pitch, fine pitch, FM, AM, etc. And that is the way I came up with figuring out the role that the struct plays in each case, and the parts-to-whole relationship of elements to the main struct. The example is definitely oversimplified, but that way of looking at it has really helped me to begin fighting my way to a better understanding and less crummy code. So if we have our struct that's like our module, delay, oscillator, filter, or whatever, and the elements are like individual settings, interacting with aleph requires the ability to change settings dynamically over time. We need functionality, and in C, functionality can be achieved with functions. I have used functions a lot, and for me, these were a bit more obvious than struct. On this site, I think we have a pretty good example of what a user-defined function is, and how it works. So in a basic C program there is int main, the main function, and users can also create their own functions to unlock some kind of functionality, or to process some kind of data. These helper blocks of code can run specific tasks, and can be called from within the main function. So for aleph, we have our module, struct, and we have our elements, settings, and we can use functions to change the settings dynamically over time. The next thing that we need to do is talk a bit about function prototypes and function definitions. So in a basic C program, kind of going back to our example on this page, all of our functions are sort of included in one.c file, so there would be a main.c file, and that would have all of the component functions in it. Once programs start to get longer and more complex, it seems to be a common practice to separate programs across several files by functionality, and to keep things more readable and better organized, function prototypes, which we will define in a minute, are kept in separate header files with .h file extensions. Doing a simple Google search brings up a good, concise definition, and it says a prototype only contains the declaration, like an overview or index, while the definition contains the actual implementation, along with the code, or other functions, that make it go. For me, it's often more helpful to look at the index like .h file, to find out what is included, and then look at the .c file to see how it works. So, bringing this all back to the topic of today's video, the state variable filter. I would first like to have a look at aleph-DSP. So the first thing I want to do is look at the index like .h file, and get a sense of what is in here. And there is a typedef struct, which is like the container for the functionality of the filter, like what the settings are or what the components of it are. Then there are the associated functions. For example, in order to set up an instance of the filter, we would need to initialize it using the initialize function. To change the cutoff, we would need to set the coefficient, and to change the resonance, the dedicated function for that. So this .h file provides examples of available functionality. To see how each of these actually work, we would need to look at the companion .c file. Oftentimes, the .c files contain more comments that can help to get things figured out too. So we know that we want to make a state variable filter. We also have an idea of which parts we need to pull in from the aleph-DSP directory files to make it work. So, before going any further, I would just like to talk about what a state variable filter is, because I didn't actually know what an SVF was, and I just happened across this while looking at some of the existing modules for inspiration. I found this great definition. So basically, the design of the SVF lends itself to allowing low pass, high pass, and band pass, all being available simultaneously. So essentially, it's like 3 or more filters in one. Looking at the aleph SVF code, there is a notch filter, and I think maybe one more type in addition to the 3 types mentioned in the definition. This time, I built the program around the 3 mentioned in the definition though. Low pass, high pass, and band pass. I wanted to try making a filter that took one input and gave you 3 separate outputs, one for each filter type. And this is really cool, because instead of just having just a low pass, or just a high pass, or just a band pass, we can get a 3-in-1. I'm sure that there are more nuanced methods of using an SVF, but this being a new concept for me, the first implementation I thought of was the 3-in-1 filter. The next thing that I'd like to do is look at the mixfilter.c code. As with every other time so far, I just used the basic mix.c file as a template and added the SVF functionality. Sort of going back to our discussion of implementing the pre-built code from aleph-DSP. Even if conceptually it can be understood, the problem for me often becomes implementing it in terms of syntax, and syntax is still very difficult for me at this point. As with past cases, I decided to investigate other modules for an example implementation that I could use as a guide. In this case, the best example came from Lines, because Lines actually implements an SVF, actually a couple SVFs, as part of its functionality. I also used monosynth because it also has an SVF. But especially for the setup of params.c and params.h, I heavily relied on Lines. The first thing in terms of looking at mixFilt that I would like to do is have a look at params.h. Okay, so the first thing to kind of point out here is that there are a couple extra entries. I've set some preprocessor directives, which are indicated by #define. I took these directly from Lines params.h. And we have param_cut_max and param_cut_default, and those are related to the filter cutoff. Then param_arq_min, param_arq_max, and param_arq_default, which are, basically, related to resonance. Then, at the bottom, I added two parameters. One is my filt, and the other one is my FQ. So the first one is for cutoff, and the second is for resonance. So next let's look at params.c. So I have set up the two parameters that I made. We talked about common parameters previously for eParam type bool. There is actually a dedicated parameter type for SVF frequency, and that is the eParam type SVF frequency, and that's what I used for my filt to control cutoff. These values are taken directly from Lines params.c. Then, for resonance, I have these and we talked about them a minute ago in params.h. All of this also came from Lines. Okay. So we have our parameters, and now I would like to investigate mixFilt.c. The first thing to point out is that we need to include our header file, our filter svf.h file, in order to access the functions and component parts of the SVF code that we want to use. I've also included Rick's tricks. I'm not actually using it though. This is a different Swiss Army knife type header file with a lot of really interesting stuff in it. I'm sure there'll be at least one opportunity to explore it, and it is used a lot in other aleph modules. Okay, so I also have filter control variables, my filt and my FQ. I have another variable called ADC wrap, and I will explain a bit more about it in a minute. The other thing that I did was to create wrapper variables for each filter type. So we have our low pass wrapper, our high pass wrapper, and our band pass wrapper. I will also explain these a bit more in a minute. Also, because we want to use an SVF filter, we need to actually create an instance of one. So kind of going back to the ideas of containers, we need one in there so that we can start accessing the settings, and/or components, elements of it, and changing them with functions. And in this case, I have created an SVF filter variable called my SVF. Then, I also need to set defaults for the cutoff, my filt, and the resonance, and I'm using the setting we talked about in params.h. We also need to use the initialize function in here to set up our module, or container, my SVF. This example comes from monosynth and Lines, so they do things essentially the same way in this case. Okay, so the next thing that we want to look at is the module process frame function. We were talking a second ago about ADC wrap. In the original mix.c code, outbus is used to sum all the ins and send them to all the outs, but there is also some extra code in there to lash each input to a soft volume control. They use the Blackfin intrinsic multiple FR1x32x32. Within 0 and ADC val 0, where ADC val 0 seems to enable soft volume control. In this case, I just used ADC wrap to lash in 0 to the soft volume control because, although it's not necessary, having the ability to do soft volume control helps. So the next thing that we need to do is send our ADC wrap, our input with soft volume control, through the filters. In this case, by SVF LPF next, HPF next, and BPF next. This is where things get a bit difficult for me to explain coherently. Basically, because audio is processed frame by frame, in order to process the next frame, we need these functions LPF, HPF, BPF next. Basically though, we are sending our 0 and plus soft volume control through each type of filter, and the filtered audio is sent out through outputs. In this case, out 0 is doing low pass, out 1 is doing high pass, and out 2 is doing band pass. That is great, but we also want to control the filter, specifically cut off dynamically. We also have resonance setup, and that can be used too, especially to get the filter to self-oscillate, but I am not so interested in at this time. Anyway, I actually learned a new trick for setting up control variables by looking at lines. We have the module setParams function, and, as I understand it, this is what helps to allow us to assign and control parameters with bees. Looking at lines, there is a paramset.c which houses this function and makes it easier to read. It also provides a really good example of how to set up control parameters, so that changes can be processed or handled within the switch case statement, which is a lot better solution than trying to assign separate variables and change them within the module process frame function. Here, for my filt, we have the filter svf set coef function. This is kind of complicated, but basically what it means for me is the function that sets cutoff. Then, for resonance my FQ, we have the filter svf set RQ. I got this one from bees too. It looks like there is some shifting going on, and that is a topic that will probably require a bit more study on my part before I attempt to explain it. So finally, I'd like to do a simple demo of mix filt. Basically, I have one in that goes to the 3 outs, one from each filter type, connected into a mixer, and I will go through each one, low pass, then high pass, then band pass. The last part is just a little bit of wiggling, mixing the different filter types, and adding some bees magic in there. Thank you.
A hideous southwest is always a climb in aged seldom succeeded flavouring untimely. Necessity white, hour in a glaze. Break sky blue light obliquely. In a cut carpet, in the pack, a sound. COO-GE. Press in the ink and stare and tease. Put in the faint and feather and white. White in the plume. N-N. No noon back, no noon settler, no sun in the slant and carpet utterly surrounded. No pressed plaster, none. No pressing pan and pancake, not related exactly, not related. Matter in the centre of single sand and slide in the hut. No account of gibberish, no skylark utterly. Perfect lemon and cutting a central black. Not such clouding. A sugar, a lame sugar, certainly. No sobriety, no silver ashtray. M-N-H-. A coexistence with hard suckling and spoons. A coexistence with orange supper. A last mending, a begging. N-N-H-. A sound is in the best society. It hums and moves. It throws the hat in no way away, and in no way particularly at paving. The meanness is a selection of parts, and all of that is no more a handkerchief, merely and large. Points. The exchange which is fanciful and righteous and mingled is in the author, mostly in the piece. CH-N. A unity is in the meantime in a union. A branch case is exactly so anxious and avoided, and even then is it in place of blunders. Is it in the piece that makes hesitation clear? The use and the checkboard and the all color minutely. This and the chance of the bright flowers inward is not in a glance. A check is an instance, and more is indwelling. Pecked places. In the unconcise word that is ministered, and in the blame extraordinarily the centre, the whole centre is coupled. This is choice. M-N-H-. Hunger is not hurry and a silence, and no more than ever it is not so exactly, and the word used is there. T-S-W-H-. A cut in trusts and in black colours, which are not carpets, not at all likely carpets, and no sucking in substance of the sacking, placed only in air outside. This makes a change precious, and not odd in place of more use, not odd in the meaning rapidly.